But let's talk some more about thermodynamics. So we're moving along here. Any questions about anything, by the way? Okay, good. And so we're in this topic 3D, which pretty much means nothing to me, but it refers to the book. And this is, they call this concentrating on the system. And what by that, we mean that we're going to look at, we have our system. And of course, there's the surroundings. And chemists will probably using, because we're sort of aiming towards our friend the Gibbs free energy, the one that chemists use, constant temperature, constant pressure. And so you have the surroundings, and they're, they exert a pressure on you, and there's a temperature, but you're in contact with the temperature, and also you're in contact pressure-wise. So if you're the system, your volume isn't fixed. If you're a chemical reaction that involves some gas, then the gas that you give off, if you have a lot of roommates, that's not desirable. But in a reaction, perhaps it would be. It increases the volume, right? You're doing work against that. But when I say concentrating on the system, we can use the system variables like S, U. We had A and we have G, and all these state functions, and just and the temperature, the pressure. Pay attention to those variables without having to always include the surroundings. And so, another way of thinking this, of thinking of this, is that we have prices with tax included. And what that means, and of course, it all boils down always to the second law of thermodynamics. Like, if something can happen, it has to increase the entropy of the universe. And in the idealized limit where it's reversible, the delta S of the universe is 0. So that's a constraint on us. But if something has like the desire to happen, to anthropomorphize our chemistry, right? If I have a reaction that wants to happen spontaneously, a part of that, big part usually, is what happens to the entropy of the surroundings. But we're using thermodynamic functions that take that into account. So when I say delta G is, and I'll write this down, but when I say delta G is negative for this reaction, it has baked into the G the fact that there's heat being exchanged with the surroundings, and there's work being done on the surroundings. So that's what we mean, and Atkins and his co-authors call this concentrating on a system. Okay, so we can go through a little, and we keep thinking, we keep going down the same lines of thought. So we have this as kind of the definition. Yes, question. Yeah. Oh yeah. I think we did. A is the Helmholtz. I think I mentioned this. It's possible I didn't. I'm going to go through these soon. And A was U minus what? Helmholtz. Helmholtz, yeah. Did I define that yet? We have the, so we know about G and we know about U, and there's also this A. If I will talk about it. I just mentioned it earlier. If I did indeed mention it, but I will mention it again. So we can leave that off if you haven't, if I didn't in fact mention it. Okay, so here's this very fundamental thing. If my system entropy changes, so we have this idea S is a state function. We can have all kinds of different ways of changing it, and it doesn't depend on the path. But if I do want to figure out how entropy of my system changes a little bit, it's a differential statement here. So I figure out what the temperature of the system is, and I have a temperature. I add a little bit of heat, and I do it reversibly. I say dq reversible is a positive thing at a given temperature. That's how the entropy of the system changes. Okay, there's other ways we can do it. So, and that's an equality, right? And the second law says that in general, that this is some other change in heat, and we talked about this probably too much. The irreversible expansion of or compression of a gas, more heat. The heat exchange is different than it would be reversibly. So if V is a constant, right? I have du, right? Let's not invoke that yet. Okay, so I have du is dq plus dw, but if and dw is minus p dv, right? Oh, okay, so I see why you're confused about the Helmholtz energy, because I'm about to mention it. So if dw equals, I have to put the proper, so if V is constant, so we're just sort of imagining now we fix that, then dw is equal to 0 because dv is 0, right? So for a constant volume, I have my du equals dq, right? But let's go back. But my dq is less than or equal to TdS, which comes from here. Okay. And minus signs minus signs are dangerous, but so are inequalities. You got to make sure that when you do just a word of advice, from someone who's had their fingers burned, like don't stick your finger in the hot oven, right? Be careful when doing algebra with inequalities. So I hope I did that right. So dq is less than TdS, right? So TdS is greater than or equal to dq. So if I have du, right, it's going to be let me get it right. So TdS is going to be greater than du in this case, right? So du minus TdS is less than or equal to 0. And I'm imagining T and V are constant here. So now I can define A. Now here it is. It's defined as U minus TS. And I'll spell it. I'll use my best handwriting here. This is the Helmholtz free energy. Helmholtz probably has an interesting life, but I don't know anything about it. But he got this named after him, and this means dA is less than or equal to 0 if T and V are constant. So what I've done is I've concentrated on the system, and I have defined something A, which is the Helmholtz free energy, and like for a finite process, delta A is less than or equal to 0 for a spontaneous, and I'm using this language. I haven't necessarily define what I mean by spontaneous, but you know what it means. Spontaneous means irreversible and allowed. Okay, so this is an irreversible process. So it's sort of a synonym with that. So, like if I'm a physicist and I like expensive equipment, you know, because that's the difference between physicists and chemists. The chemists just have a bunch of glassware. You know, they break it, they get another one, right? And so, but the physicists, they might have something that has a constant volume, some chamber or whatever. And if they're doing all their stuff inside of that apparatus that had a constant volume and then a controlled temperature, constant temperature, then this Helmholtz free energy would be sort of what they'd be interested in looking at, right? And but for chemists, right? We have T. Let's say we have T equal constant, and now we have P equals constant. And you know, I hope you realize you can have one or the other. You can have T, or let's say we T is constant sort of throughout this kind of discussion. The alternative to having T constant would be let's hold the entropy constant or something like that. I mean, you'd have to be a pretty rich physicist to have an apparatus with an entropy knob on it, right? Heating coil or whatever and a thermometer, they're a lot cheaper. So controlling the temperature. But if you have volume versus pressure and there's any kind of gases involved, like blocks of metal, it doesn't really matter. They don't change their size much when you increase the pressure within reason, right? Even Superman doesn't change the volume of that lump of coal very much when he squeezes it into a diamond, right? You know what I'm talking about, right? But when there's a gas, then if the volume is constant, the pressure's not. And if the pressure is constant, the volume is not, because there's all kinds of expansions that go on. But if I do this, then I have my dq is dH, right? If I had volume constant, du is dq, but if I have pressure constant, then dH is dq, and more heat is going in because there's some work being done, right? And my ds, is greater than or equal to dq over t. And so what this tells me is I'll have my dH minus t ds as being less than or equal to 0. And so now I can define this one, and this one needs no introduction in this audience, unless there's some physicist that sneaked in, right? This is the Gibbs free energy. Gibbs was one smart guy. He came up with a lot of very important ideas very early. So I know he had an interesting life, but no time for a history lesson here. And this is the one that you've seen. And here T and P are constant. And I can calculate dG, right, is dH minus T ds. And that's what this thing was. So T and P are constant, right? And so, so G is useful when T and P are, let's say, controlled. So like you decide the atmosphere is, the pressure is 1 atmosphere. I have open beakers and stuff, and the temperature is, the room temperature. And whether the room temperature is comfortable or not depends on where you are in the budget of that institution, right? So, but you could also control it. The organic chemists have these fancy things that they use to heat up things, and you could have a heat bath and do some biochemical reaction in whatever it is, 37 Celsius, whatever you would want to control, or you could do it at room temperature. Depends. But if you want to know if something happens spontaneously, the change in free energy being negative, and you've been hearing this story since high school, right? Did everybody see this even in high school? I probably saw it in high school too, but I do not remember much about high school. It was in Nebraska, so I can't. There's some stories I can tell, but even I won't tell those stories. All right, and the deal here is, like DG. Let me emphasize this. DH minus TDS. And saying this is less than or equal to 0, this is really about I've said this probably too many times, but I'll maybe prove it here. It's really about ds of the universe being less than or equal to 0. Because, my dH, and I'll write it like this. So I've got my system, and my surroundings, and the surroundings there's an external pressure, right? P external is equals the lab. Let's say it's 1 atmosphere, okay? But my things are in balance, right? So my P is equal to P external. So I'm just sort of drawing a cartoon here of this situation. And there's some Q that goes into the system, right? So Q is the heat that goes in the system, and dH equals dQ if the pressure is constant. du is dQ if the volume is constant, right? So I keep saying these things, but dQ equals minus dQ surroundings. This is, this is, you could say this was the first law, but it's just the obvious thing that, if heat goes into the system, it came out of the surroundings. So ds surroundings is equal to dq surroundings divided by t, which is equal to minus dh divided by t. Right? And so here, this is the tax included part, right? So my dg is minus t ds, right? Usually I write it a different order. But this is equal to minus T and ds, but dH dH is minus T ds surroundings. So if there's a minus out here, so I put it plus ds surroundings. Right? So dG is really minus T ds of the universe. So its true nature has been revealed. You now know actually what you are paying in taxes. This is, this is something that usually you don't want to worry about it, but when it comes time to actually vote or something like that, then you want to know how much tax you are paying. And you can see that DH term is really there for keeping track of the the entropy change of the universe. So H is H has the units of energy. It's a Helmholtz, or they call it the enthalpy, but it's something like an energy. And you have this idea that if I have if I have a mountain range, a ball is going to roll, and it's going to end up down here at low energy. So this is an intuition that you have water. Water ends up, in a volcano's crater. There'll be water if it's not erupting, right? There'll be some water in the bottom of. There'll be a lake there, Lake Tahoe, things like that, and things like to go to a low point in energy. Why? Why would that be? Energy is conserved. Well, what's really happened is it's gone. If you want to think about why energy comes into this, as your ball is rolling around in a bowl, okay, and eventually it stops, okay. There's been some friction going on, right? So something has happened to the kinetic and potential energy that physics conserves, right? Now, you probably took a physics class where you might add a little friction, and then, you can calculate the harmonic oscillators time dependence, and it kind of decays, right? Maybe you have this idea. What's happening is you're losing energy to the environment. Heat is going in to the environment. And so what's really happening is the entropy of the environment's going up, and that's why you're settling down to this point. And this shows you this thing that chemists always use. It's sort of true nature. And so when I say dG is less than or equal to 0, really saying ds of the universe is greater than 0. That's an S, by the way. People actually, the hard part about being a scientist is, this is why privacy, someone might be reading your emails. So for a scientist, you say, please read something that I wrote. That's mainly what the case is. But when you teach a class, sometimes people do read what you write because, they have an interest in it. So this equation here really is saying delta S of the universe is equal to 0. So, okay. Concentrating on the system means I can use G, and it's taken into account that tax I have to pay, and it's the delta H term that's kind of in control of that. Now, I think I'm going to skip something, but I'll draw your attention to it. There's something called the maximum work. And I'll just give you. I think the book is confusing about this. And that thing called A, which was the Helmholtz free energy. And so if I say what is the maximum work that so the max the work out maximum and is actually minus delta A. This is what I think makes more sense. Maybe I'll give you a problem. Like I have some process where a gas is doing something, and I say, what is the maximum work I can get out of that process? Okay, out. If it's a spontaneous process, delta A is going to be negative, right? So I calculate delta A, and then I change its sign. I want a positive thing, and that's what I can get out of it. So I look up a chemical reaction, and I calculate delta. I can calculate delta G, delta H, all those things. You can also calculate delta A. And you can look at that and I can say, okay, if I make a battery out of this reaction, this is how many iPhones I can charge with it, things like that. But this thing is typically negative, okay? And if I, because this is from the system perspective, so I don't want to say any more about that except mention one thing. So A. Why did they choose A for this Helmholtz free energy? H was taken. Why they used H for enthalpy? I don't know. It's the fourth letter of the word, so that can't be why. Even a nerd would not do that. The German word for work. This is the German word for work. And it's related to this thing, Arbeit. Other books will call this F. You'll sometimes see F equals H minus TS. Another notation. So there's an infamous place where you see the word Arbeit. Does anybody know what? And it's kind of timely, actually, in these times. It was one of the concentration camps had a sign above their gate. Said Arbeit macht frei or something like that. Work will make you free. It's a very cynical thing to put there, right? But of course, people keep trying to steal it. It's sort of a souvenir in ways. But yeah, so this word shows up probably most famously above the entrance to Dachau or something like that. But okay, so we'll again stop our history lesson and keep moving here. Okay, so let's go back to Gibbs free energy. This was an energy that was made in the USA, right? Because he was at Yale, and anyway, he's buried there. If you ever go to Yale, you can look around in some cemetery and find him. DG, so DG is less than or equal to 0, and T and P constant. There's no point in trying to write in a hurry doing this because you just have to erase it. And for finite process, and G is H minus TS. And so delta G is delta H minus T delta S. So we've gotten to something that and it took a while, didn't it? But this is true if T is constant. Because there's all these differentials everywhere, right? And if somehow T is changing, then it gets more complicated. But the T is just sitting there not changing, and so I've got these two contributions, right? And so there's two competing parts. Right? There's this and there's this. And so, delta G negative so it favors, well, okay, so like let's say delta S was 0. So something happened, it didn't change the entropy of the system. And remember, we're looking at the system. This is potentially confusing, but if I see a G, an H, or an S, or T for that matter, and P, but T and P are constant and they're equal. T and P are equal between the surroundings. The external pressure is P, and the external temperature is T because we're in an open beaker in thermal contact. But all these letters I'm writing refer to the system, right? To the thing that's inside of what I write when I say system. But I want this to be negative, so I can have delta H negative, and I can have delta S positive. But I can play games with how I balance those two things. So I can get away with delta H being positive if I compensate for it with my delta S being negative enough. So delta H negative, and here's one of those questions I could ask. Delta S negative means, you see, this is what I'm talking about. That heat goes, fill in the blank, the system. Oh, let's change that word. So we talked about naps in kindergarten. Now we're in maybe 3rd grade. Well, they do this in other classes here too. Fill in the blank. So what are the choices? Maybe I can make it multiple choice. So I could say into or out of. Which one is it? Huh? So, I'm talking about the surroundings, okay, for one thing. So delta H negative, what do chemists call this? Delta H negative. That means heat comes out. Like something exploded in the parking lot. Someone's car catches on fire. It's exothermic, right? This is exothermic. So this is going into the surroundings, right? Delta H negative means heat goes from system to surroundings, and so here's what heat is doing. Here's the system. I hope that picture evokes something. I don't have to write it out. Heat is going into the surroundings, right? And so, does that make sense that you'd want that to happen? Why would you want to, like if you want something to happen spontaneously, why would you want to put heat into the surroundings? Delta S surroundings is going to be, minus delta H over T. And that's going to be greater than 0. So that first term is the tax. You have to make sure that you give off enough heat, okay, so that whatever else you do has delta S of the universe be negative. And so heat going into the surroundings is good for the spontaneity, right? So, pardon me? Oh, because like dq is equal to dH if pressure is constant, right? So this is the system. so if I draw my system, and so there is Q. What happened there? All manner of interesting things can happen with this pen. So there's Q being positive, right? So that would be and if I kept doing that and I integrate with that, that would be, delta H greater than 0 means Q is greater than 0. Heat into system, right? Delta H less than 0, Q is less than 0, Q surroundings, which is minus Q, is greater than 0. Delta S of the surroundings, which is Q surroundings over T, is greater than 0. Okay? And that, delta H less than 0 is what everybody calls exothermic, except one person. What does Shaka call it? If Shaka, I'd have to talk with him. But Peter Atkins calls it exenthalpic. Okay, find somebody else that calls it that. I mean, a normal person, not Shaka, not Shaka. Does he call it exenthalpic? Is that true? It's what? Ergonic. Where did he get that one? Okay. See, this is what I like about chemists. Anyway. So I'm going to call it I'm going to call it exothermic because I don't exenthalpic. It's one of those things that I don't know. I sometimes hear things and then I look them up and I regret it. Okay. And this could be one of those things. It sounds like that. Okay. So how can something how can something be endothermic, right? So if delta H is greater than 0, that's endothermic. And this means that delta S of the surroundings is less than 0. So, the rest of the universe is going in the wrong direction as far as the second law of thermodynamics, right? Because, Q is greater than 0, Q surroundings is less than 0 because it's equal to minus Q, and that's negative. So that does not favor the process, but we can get out of it because we have minus T delta S, and this needs to be negative, right? And if it's negative enough, then we're okay. So an example of this, and I bet you've all done this. Do they still do this? Do people still come in contact with the physical world, or is it all virtual? I don't know. Okay, I'm old-fashioned. I still walk my dog in real life, and I have the green bags in my pocket to prove it. So anyway, so just watch that. Anyway, be prepared. I was a Boy Scout. I made it all the way to first class. Okay. Anyway, be prepared. So. But in some class, in fact, more than once, I remember holding a beaker, and I put in some powder, into this beaker. What is this? And I stir it, and it feels cold. Did that ever happen to you? Yeah? Okay. So you have some solid in here, right? And it's got, you've got these, it's a salt, you have ionic bonds, opposites attract, you have a positive thing, a negative thing, a positive thing. So they're energetically, they're pretty happy, aren't they? Right? But nonetheless, so that it sounds like they're going to stay together, right? You predict that, what is it, Harry and Meghan, are they going to stay together? There's all these things that you could make a prediction, but you could be often wrong, right? And this happens. And when that happens, heat goes into the system, which lowers the entropy of the surroundings. That doesn't sound like it's going to be helpful. And then I take all these mechanical, or these bonds between things, and I break them asunder. That's not going to be helpful either. Now, of course, what happens to ions when they're in an aqueous solution? Well, so I have an ion here, and I have an ion in water. What do the water molecules do? Do they say, I don't care? Well, they solvate it. Okay, so you do get energy out of solvating an ion, right? So I'm sort of leaving that. But what? So here, delta S of the surroundings is negative, but delta S is positive, because what I've done, I've taken an organized thing, that solid piece of material, and I've disorganized it. And if I ask, how many ways are there to put these ions into a lattice? I mean, there's not one way, because there's many permutations, right? But they are indistinguishable. So there's all kinds of interesting quantum mechanics and statistics. Non-trivial but fascinating problem. I hope you all study it as graduate students in theoretical chemistry, but I'm not going to get my hopes up. But anyway, but there's a lot more ways in the liquid. Okay, so delta S goes up, and so my delta G is delta H minus T delta S. And like if you're trying to cook, is it a good idea to cook? It certainly saves money. But let's say you are trying to dissolve some sugar in water, it's not dissolving. What is an effective way to increase the rate and all the extent of the solubility? Rate does not what we're talking about in thermodynamics. What do you do to something to make it dissolve? Yeah, heat it up, right? And there's a T here, right? So if I were to graph this, if I graph delta G, and I'm going to draw a line here, this is 0, right? And y equals mx plus b. Do they still call them m and b? Okay, that's good. So there's a slope and there's an intercept. And this equation does not work forever. Zero temperature, we'd have to do something else. But if the T, so I have delta H greater than 0 and delta S greater than 0. And so what is the sign of the slope of that function as a function of T? So I've got minus delta S as the slope. M equals minus delta S. Delta S is greater than 0. So there's a negative slope. But the intercept is positive. So I'm going to have a line that looks like this. So this is delta G as a function of T. There it is. So there comes a point, call it T sub C. And if over here delta G is greater than 0, and over here delta G is less than 0, and right there delta G is equal to 0. And so if delta G was equal to 0, it would be reversible. It would be at equilibrium. There would be if I was at that temperature and I was trying to dissolve sugar, I would have solid sugar and sugar in solution, and the concentration comes into play in this. But solubility, as you probably know from hard experience, solubility depends on concentrations, right? But there's an equilibrium established. If I go above that, it'll all dissolve, and if I go below that, it'll mainly precipitate out, right? And if I have water, if I have liquid water below a temperature and water vapor above a temperature, right at some temperature, I have an equilibrium between water vapor and liquid water. I'm thinking in a closed container. If it's open, it'll eventually evaporate anyway, right? But I'm thinking about a little bit different situation. But so you can see that low temperature. So I have to reach a temperature for it to happen spontaneously. And that's why, as I heat up, the solution eventually will dissolve. And I can even find this T sub C by looking at delta H divided by delta S. We'll do this kind of thing later. So you can look up in thermodynamics. Maybe you did stuff like this in general chemistry. You look up in thermodynamic tables at the change in enthalpy of something, and then you look up the change in entropy of something. Maybe you infer it from looking up the delta G. And then they say, what is the boiling point of this stuff? Okay? And then you did something like that to get it. We'll come back to that. But okay. Okay, I have 1 minute, and so I'm not going to say anything else. But we'll stop now. It is Friday. There's reasons to get on with our day. We should have the exams on Monday for you. Yeah, okay. Don't worry, just relax. Watch some Monty Python to get yourself in the mood.